We will now explain to you the mathematical concept of transform densities. Since working through the lecture slides, the script and the internet material to understand how to transform the function was a big pain for us, we will try to conduct things a bit more detailed in order to make you tick off this formula for the rest of your life and create 9 minutes less of an experience like this and more like that. So let us slightly jump into it with a quick recap on how to handle integrals, derivations, their notations and some related mathematical objects. Then we will derive the substitution rule for integrals and finally get a hold on the density transformation itself and then later look into an example. This is a function and this is an integral. The detail here tells you with respect to which variable to integrate the function. For most of the time we ignore it because we simply do not have any options which variable to select for this purpose. It changes if we think about using another function, as for example this one. Over here we would now do it with respect to v. The stylized cursive d might in fact rather be known to you from another expression, the difference quotient. The quotient is what we call this term. The difference quotient was born when a prehistoric natural scientist, Newton, started drawing triangles into our graph to determine the slope of the function. Although he tried to be as precise as possible, he lacked accuracy. So another guy, named like a cookie, Leibniz, started to approach it in a more abstract way using the derivative. So this is a notion he used basically for the same thing. And just to confuse everyone, a third guy, Lagrange, decided to give it an additional label, that one. So in practically computing all the graph's slope is easier than remembering all these names. So following the rules of derivation, constants become zero, you display some of the numbers keeping the power, product and quotient rule in mind, and for exponential function it goes like this. And if now someone asks you what you were doing, you just explain them that you used the chain rule. If we attempt to do the same thing backwards, we call it the antiderivative with a capital letter. Remember to not forget about the constant. One very last thing to prepare you for the upcoming proof. Anyway, what is the composition of two functions? Say we are working denoted by a little intimidating integral. But for computing this nexus, we rewrite it now want to set this in a part and everyone knows what to do. Variable u. Combining this equation with Leibniz formulation of a derivative, it now yields the differential form of an integral. Now we have the opportunity to change our integral in a way that we substitute every occurrence of x by an equal formulation containing only u. Now we can finally calculate the integral and resubstitute. Oh, and by the way, there is a restriction that not tells you whether you are correct or not. Double checking the results by computing the derivative again. I know what you're thinking now, but just hold on with me for one more minute and we will use an actually everyday life example. What we just did is defined for a general case and therefore we write this. And here is our substitution and it yields again this and as well as that. Formal evidence for our equation arises from the composited function of phi of x and the antiderivative of f. So now applying the chain rule, it delivers this. And finally, we need to integrate on both sides of the equation and reshape the formula. So, and now our proof is done. But we need to add that the restriction from earlier on the functions we are allowed to use now implies that phi of x equals u is strictly monotonic. So for increasing x, also phi of x is always increasing. So now let's apply that onto a serious problem, and we're back in the trash. So yeah, Luca, Sasha and Lisa spend some more hours philosophizing about discrete probabilities. The probability density function, p of x, assigns to every alcohol level x its corresponding likelihood, L of x, and the integral over p of x gives the probability, px, of a range of alcohol levels. So the bartender knows for sure that they are going to have a tough time to find the exit. And he's so friendly that he can even draw a corresponding function, gx. From his experience, he can tell that the amount of visibility of the exit correlates with the alcohol level. G of x assigns to every level of alcohol x a value of visibility, y equals g of x. Given these two functions, we want to compute the probability distribution of the visibility. And you may pause now to apply the density transformation yourself. From y equals g of x, we derive the desired substituent x equals g to the power of -1 of y. So if you did everything right, this is the solution formula, and you probably did it right because you're amazing! And here now you can see our sources. Thanks for listening, everyone. Stay tuned and see you tomorrow.